Welcome to this lecture on field programmable logic arrays, gate arrays in the course Digital System Design with PLDs and FPGAs. In the last lecture we have looked at the clock tree, essentially some basic related to the clock tree, why the clock trees are special clock trees are required, and we have analyzed the basic timing of data path and sequential circuit in the presence of skew, and then that is a kind of setting the background for the clock tree, which gives minimum skew between the endpoints. And then we have looked at the special resources like DLL, PLL, clock managers and all that, and we have started the various method of configuring or programming the FPGA. So before continuing with the configuration or programming, we will briefly look at the last lecture's portion, and then we will get on to today's part. In the last lecture we have looked at basically the issue of metastability. For a flip flop not to get into metastability, the input has to meet the setup and hold time, and for a data path or a register to register path, from that requirement we develop the inequality for the minimum clock period, and we develop the condition for not violation of the hold time. Okay, and same thing with the sequential circuit or FSM, where the register to register path is between the state registers. Expressions are same because if you kind of show it explicitly, separate the source and destination, it exactly looks like this. Now what was missing in this analysis was that we assume in all these arriving at this expressions, we assume that the clock is reaching at the source and the destination at the same time, which cannot be true in a chip. Depending on which way the clock flows, the destination could be lagging or leading the source in terms of the clock arrival. So that should be taken into consideration when analyzing these expression, and that is what we have done, and we have set two conditions or two scenarios where the clock and the data flows in the same direction, which is called a min path problem, and where the clock and the data flows in opposite direction. And we have looked at the case where the clock and the data are in opposite direction. Then in that case the source clock is kind of leading, or the destination clock is lagging. So the available time for a register to register path is reduced by amount of skew. So T clock minus T skew has to accommodate TCQ, Tcomb and T setup. So in essence the clock period requirement goes up and the frequency comes down. So because of the skew, the frequency of operation is coming down. In the opposite problem, in the min path problem, where the source destination is receiving a clock which is a delayed version of the source register with respect to kind of as far as the skew is concerned, and in this case looks like the register to register path from one clock edge to the next clock edge, we are in a better position because you have T clock plus T skew is the kind of time available which need to accommodate this path delay. Okay, so if you analyze from one edge to the next edge, things looks pretty comfortable, because that is easier on the budget. If you would have fixed the clock period or something, then here is a relaxation on the clock period, so which is good in a way. But the real danger, as I said, is that since the clock is getting skewed, maybe this if this the data path is fast, then it can violate the whole time because the clock is moving ahead, and if the TCO and TCOM is min, then it can violate the whole time. So that is what is shown here. TCO min plus TCOM min should be greater than the T skew max and T hold. So if it is not so, it can violate, and if there is a violation happens, kind of reducing the clock frequency is of no use, okay, because in the earlier problem we sorted out, suppose we have a clock period which cannot accommodate this kind of skew, then we can reduce the clock period. But in a min path problem it is not related to the clock period at all, because we are talking about the same edge of the clock, okay. So it between the same edge of the clock or between the edges which are delayed, same edges which are delayed by the skew. So the only way if there is a whole time violation to avoid is increase the combination delay or the logic delay. So in essence clock when somebody is routing the clock in a chip, if there is a relative delay between the endpoints, okay, wherever it is, that is troublesome, that can reduce the clock frequency, that can create whole time violation. So there need to be a mechanism to kind of route the clock tree such that the relative delays between the endpoints are minimal. So that shows, with respect to earlier picture, we cannot route like this, you know that as the clock tree goes, it gets, everything gets delayed because of the loading, and from this end to that end the delay is very high. So we cannot have such kind of arbitrary scheme of clock routing. The ideal thing would be that from the clock pad to any endpoint there should be kind of equal length of the wire and the equal number of buffers. Now this scheme does not even help, even if you insert buffer here, buffer here and all to kind of offset the delays, offset the loading. That does not help because the buffer delays add to the skew. So you should have the buffers which are balanced. So it is ideally like, in a simplistic way, you can put a buffer, then branch, another buffer and another branch, from the main route one more branch with the buffer and so on. So that the extension of that is the H clock tree, where from the input point you go horizontally branch, then vertically branch, then horizontally branch. Wherever there is branching, then you put a buffer, okay. Now that does not mean that this is just one endpoint where a single flip flop is connected. There could be some kind of, depending on the buffer capacity, there could be 20 or 25 or so many, depending on the buffer, so many flip flops are there in these branches, in the last branches, okay. But like if you have a order of magnitude increase in the number of flip flops, then you branch vertically, each one from there you can go different vertical branches and so on, okay. And the idea is that if you take from, say, take this endpoint and this endpoint, and if you count the number of buffers up to the endpoint and take the length of the wires, it will be identical. So the relative delays between the edges, between the endpoints will be minimal, though from the kind of the input to the output there could be skew, quite a bit of skew, which is not much of a problem. If that is a problem, then I can introduce a DLL which compensate for that kind of delay, okay. So that is what is the DLL is used. Suppose you have a clock tree which is getting loaded, and because of the loading if the clock is delayed and if there is a skew between the input clock and the output clock, then the DLL can avoid that, because from the output there is a feedback to the input and there will be definitely delay, a skew, but how it is compensated is that the T clock minus T skew delay is kind of further added into the tree, so that this edge will come in kind of sync with the next edge, okay. So the delay lock loop kind of synchronize the edge by further delaying already delayed edge, that's how it works. Compared to PLL, in a PLL essentially the scheme looks similar, you have the input clock and the feedback clock, but what is done is that the phase is compared and the phase difference is converted into a voltage with a low pass filter and or some equivalent scheme, okay, and a voltage control oscillator synthesize a clock frequency which is not the kind of delayed version of this input clock frequency as in the case of DLL, but in a PLL a new clock is synthesized, okay, in phase with the input clock, and that has certain advantage in the sense that like if there is a jitter in the input clock in a delay lock loop, that will appear as a jitter at the output because delay lock loop just delays the clock, but in a PLL since it is synthesized and there is a filter which kind of filters out the minute jitters and the clock is kind of stable, okay, it is a new clock. It would not have the distortion of the input clock or the jitter of the input clock. So that way PLL is better, but then that the PLL always act with kind of with a range of, there is a lock range and there is time to lock and things like that, at the beginning when you start up the PLL has to get into lock, so it takes certain delay for the PLL to come into lock and all that. So that is about the PLL. So in the current FPGAs as PLL digital clock manager which is composed of DLL for deskewing, phase shifter, frequency multiplication, division, and this gives phase shift like 90 degree, 180, 270 and all that. There are clock buffers, muxes for clocking, clock switching, and that has to be glitchless, when it has to synchronize the edges, so there will be synchronizing flip flops which synchronize two clock sources to each other, and all this can be connected in the clock path or clock tree path. So that is what we have discussed, and this can be, all these special resources can be instantiated from the vendor library using the code generator tool. Sometime synthesis tool will infer from the code, sometime you have to write the VHDL attribute along with the code to help the synthesis tool to kind of infer what is going on and to kind of instantiate the correct component. Then the last thing we have looked at was the configuration or programming of FPGA, and this the first thing while prototyping, the most suitable method is through a synchronous serial port called JTAG, which is used for PCB testing, chip testing and all that, which is used for FPGA configuration also. So there will be a small dongle connected to PC which can program the FPGA, and then there is a serial mode where the FPGA clock a serial prom and get the data and programs it. Slave serial exactly like master serial, where in the slave serial FPGA expect the clock as input and the data in synchrony with the clock. Normally this works in conjunction with the master serial for a kind of chained programming of the FPGA, and the select map is a byte wide or kind of programming 8 or 16 bit. Usually when there is a microprocessor through a parallel bus, FPGA can be programmed, and the configuration bit stream can be stored in the memories of the processor, okay, wherever it is located, maybe in a flash on the board, and from there along with the firmware it can be stored, and at the startup the CPU can program the FPGA. So this shows a serial configuration where one FPGA is a master and another FPGA is a slave, which is configured by some mode pin. 3 mode pins are there. In the current FPGA there are only 2 mode pins, and see this is in the master mode and this is in the slave mode, and you can see there is a serial PROM. The clock for the serial PROM is given by the master FPGA. Also the slave FPGA get the clock from the master, and the data from the serial PROM is connected to the data input of the master FPGA, and there is a data output of the master FPGA which is connected to the data input of the second slave FPGA. Now if you have a third FPGA, what you can do is that the data out of the this serial port can be connected to the data in of the third FPGA and so on, and you can combine all the bit stream of all the FPGAs and store in the this particular PROM. At the beginning what happens is at the power on the FPGAs start programming, and or if there is a program pin is there, if the program pin is made low, and if you kind of apply a negative 0 pulse, then it starts programming anytime. One issue is that at the beginning these FPGAs has to clear their configuration memory, okay, because it could be not a power on programming, it could be a reprogramming of the FPGA while the power is on. So all the program memory, configuration memory has to be cleared, and depending on the FPGA type and the size, it will take variable time. So the question is that how do each FPGA knows that the other is completed the initialization. So there is a init pin which is an open drain output which is also sampled internally. So it is an IO pin which is open drain, so and which is pulled up. So it is like it is forming a wired AND, okay. If everything is high, this will be high, if one of them is low, which is pulled low, okay. That is the state of this kind of wired AND connection. And what happens is that suppose if the master clears the configuration memory and it has come out, then it will drive the init output high. So but if this slave is still in the init mode, it will be driving it low. Because of this pull up resistance, this still be in low, and that is also input to this particular FPGA, and that sample that input, and if this still is low, it waits for other FPGAs to finish. So this kind of the init, which is an IO pin, which is an open drain which forms a wired AND, helps the init synchronization between the masters and slave. So ultimately everybody initializes, every FPGA initializes, and in come out of initialization, and then the master FPGA start getting the data, okay. It gives the clock, it enables the clock, and you can see that the init pin is connected to the output enable of the PROM. So even if the clock is going, unless the init goes high, this chip output is not enabled, so the data wouldn't come. So once the init phase is over, the FPGA starts clocking and get the data. So the master FPGA programs, while it is getting programmed, this D out is made 1, okay. The 1 is going there, so the slave wait for the starting pattern of the configuration. Since everything is 1, it will wait. So the master FPGA configures itself. Once the configuration is over, then the slave FPGA's configuration bit comes, and that is bypassed to the D out, and the slave gets programmed, okay, and so on. Now if the second slave, while the second slave programs, that leaves a D out with the 1, and the third slave wait. So one by one the FPGA gets programmed, and this is a pin done pin which indicates that the FPGA is kind of finished programming. Now again once again this is an open drain output, so which is pulled high, so it forms a wired AND again. Unless all the FPGAs done pin is high, this wouldn't go high. So this is an indication to the rest of the circuitry, like you will have some like maybe a CPU which is working in conjunction with the FPGAs. In that case this done pin will indicate to CPU saying that FPGA has finished configuring and normal execution can kind of continue. So if there is a CPU it will kind of sample the done pin and wait for the FPGA configuration to be over. Once it is done then it will start enabling the normal operation. Or if there is another external circuitry you have to make sure that the done pin kind of enables the rest of the circuitry, otherwise there will be synchronization problem with the FPGA and the rest of the circuit, because there is another circuit which gives input to the data, input to the FPGA, and if FPGA is not configured yet those data will be lost. So this done pin has to be sampled by the rest of the circuit, and normally we can assume the rest of the circuit is maybe a CPU or another programmable logic based circuit, whatever it is. This has to be taken care while designing. So that shows the kind of very important kind of mechanism to program the FPGA in a chain, okay, the multiple, or this can be single, it does not matter. If there is only single FPGA you can forget about this and this works. And nowadays the SPI or SPAs based the prompts can be used. So the FPGA offers instead of the custom serial port SPI port, and the SPI can work with 1-bit data, 2-bit data and 4-bit data. In addition this PROM itself can be programmed through the JTAG port permanently. So not only that, while prototyping the FPGA can be programmed through JTAG, this SPI PROM, not this PROM, the SPI type PROM can be programmed through the JTAG port, which often when you buy an FPGA board these options will be available. You can program normally a SPI flash will be connected in this fashion to the FPGA, so that you can program the FPGA through a JTAG port, this flash through a JTAG port, and if you put appropriate the mode pins, FPGA can be configured from the flash PROM. All that is possible, and that is what is written here. All what I have done is kind of elaborated, and the select map scheme where you have a CPU and you have FPGA. Normally you have a synchronous byte wide or 2 byte wide data program the FPGA, and these are the pins. You have the program, chip select, write, clock and data. This is a synchronous bus, init, done, busy and all that. Okay, now the issue with such a bus is that most processor bus are not sometimes synchronous, okay, like the microcontroller bus may not be synchronous. So you may have to kind of translate the bus protocol of the processor to this synchronous protocol. So that can be achieved by a CPLD coming in between to do the protocol translation of the bus, and we have discussed the CPLD in the CPLD part of the lectures, and we have mentioned that CPLD is good for bus protocol translation. So that is the scenario which is shown here, where the CPU has some memory which could be flash, where the firmware is stored. Now the FPGA configuration bit stream can be stored here. CPU can access that, read it, then maybe byte wide, 1 byte is read here, then the byte is written there, again read and write. Such a thing can be done using this kind of scheme, and if possible the CPU can directly write if there is a synchronous port which matches the protocol. Otherwise you will have to use some kind of parallel port instead of CPLD. That can be done, but which can be very slow sometime when you use a parallel port in a CPU, because you have to address each port, you have to use the port for clocking, which can be very slow sometime, okay. And that shows the timing, like every clock edge the data is coming, chip select and write bar is low, and anytime the FPGA is not writing the data, it will indicate the busy signal. In that case the data has to be kept for one more clock, so it is like a kind of extending the bus cycle if the peripheral is slow. I am sure that you have studied that such scheme, normally ready, normally not ready kind of system. So this is a kind of normally ready system. So if it is kind of nothing, if the FPGA doesn't require more time, then you keep clocking the data every clock cycle. If it requires, then it indicates it's not ready or it's busy, then you extend the bus cycle by adding extra delays, and this is a kind of very simple scheme which can be implemented in a CPLD. So that is what is the kind of crux of FPGA configuration. There are current FPGAs are more detailed, I will briefly mention it, but for Vertex these are the main ways of configuring it. Basically the JTAG, the master serial, slave serial, and I mentioned about SPI port, then the select map which is byte wide, which is 8 bit or 16 bit. One thing to remember is that while FPGA is getting configured, all the pins will be in a tri-state mode. So all the FPGA pins will be in tri-state mode. So the rest of the circuit kind of has to make sure that while being configured, these pins the status will be tri-stated, and it has to be appropriately pulled up or pulled down depending on your the requirement of the rest of the circuit. Okay, but the rest of the circuit is sampling one of the output of the FPGA, which normally in a default state you are assuming it to be 0, but while configuration rest of the circuit comes up before the FPGA configuration, then assume that one of the input is 0. If it is tri-stated it can create problem, so it has to be pulled down, and once the FPGA is configured all the flip flops are reset using an internal reset line, which the FPGA doesn't advise you to use as a reset. So in your circuit you want reset, even the power on reset you should implement the separate power on reset than this internal reset signal, though there is a way of using that reset signal within your design. It's a very kind of lot of flip flops are connected to it, so it's very heavily loaded, so it may be a better idea to reset it separately, which gives a good drive. So this I just briefly mentioned because there are different kind of extended version of that Vertex configuration is available in recent FPGA. So I have taken an example of Spartan 6. It is true of Spartan 6 or kind of Vertex 6 or Vertex 7 or any of the 7 series FPGAs. So you have boundary scan, which is a JTAG port which can configure a single device, or like we have seen in the serial mode you can chain the multiple devices through the JTAG, exactly like what we have seen here. Even in the JTAG there is a TDI pin which take in the data and TDO pin which take out the data. So the TDO pin of an FPGA can be connected to the TDI pin, so it can be chained. Okay, so that is possible. So you can in a boundary scan you can have a single device or a chain, you can program multiple device. In the master serial you can have chain, along with the slave you can have a chain of devices. Sometime what is required is that if same configuration has to be applied to all the FPGAs. Okay, that means all the FPGAs are of the same type and it is configured by the same bit stream, it can be connected in parallel. And now in the serial mode if you use the SPI flash, the data bit can be 1 bit, 2 bit or 4 bit. There are appropriate pins, and similarly for the slave serial. Normally as I said slave serial work along with the master serial for the chain, and in the select map you have 8-bit and 16-bit configuration. You can have a single device or you can have a chain of devices in select map. You can have slave select map where the clock is in here, the clock is given by the FPGA, but in a slave select map FPGA expect the clock from outside along with the data. Okay. So it's a little more elaborate than the vertex we have studied. So I just mentioned so that the information is current. Whatever I have talked about, the lookup tables, logic block and all that can be extended to these kind of new devices, but this is additional, so I mentioned that. And another issue with the earlier FPGAs were, suppose you come out with a proprietary design, you put the configuration bit stream in this PROM. Okay, now you send that into the field on a PCB or in a product. What can happen is that the power on somebody can capture this data, because it's very easy, because the clock is coming in synchronous, the data is coming. So this can be easily kind of reverse engineered. Somebody can read the bit stream and reverse engineer the complete system. Okay, because in an FPGA the main thing is in this PROM, and that is kind of there is no security on it. The bit stream is coming as it is, it can be easily read. So it will be worthwhile if it can be kind of protected, because mostly this will be some intellectual property of the designer or the company which is doing the design. So what is done in the current FPGAs are that this bit stream can be encrypted using the advanced encryption scheme, which is called AES, using a 256-bit key. Now through the JTAG port this FPGA can be programmed with that key, and FPGA can be told no read back. That means once it is programmed, this key cannot be read back. Also the configuration can be read back. Okay, otherwise it is possible to read back the configuration for the purpose of verification and so on. So that also can be disabled, and then you deploy that in the system. That means you program this PROM with the protected bit stream. Then what is going on, this kind of this line is an AES encrypted bit stream, and without the knowledge of the key it is very difficult to break the scheme. And this can be kind of a key can be very specific to the device. That means if a company is making, an industry is making say 10,000 devices, each 10,000 will have separate keys, not the same key. So that way it can be very well protected. So that is available in the current FPGAs. So there is an AES encryption with a 256-bit key. So the bit stream is encrypted using the bitgen tool with a 256-bit key. Encryption key is programmed into FPGA through JTAG port, and once it is programmed you can configure it for no read back, and the configuration also can't be read back. And AES key can be permanently fused, like you blowing the fuse in FPGA, or it can be programmed in an internal SRAM with a battery backed with a battery backup which is connected externally. So one can choose those options. If you permanently fuse it, you cannot change that AES key, so it will be permanently programmed. You will be forced to use the same key for all the bit stream you program into to the flash. So that way the encryption kind of protect the design. Another option available in the recent current FPGAs are bit stream can be compressed, and which is bit older than not that the Spartan 6, even before the FPGAs before had this option, because there could be a lot of resources which are not used at all, not configured at all. So there is a lot of kind of redundant information that not being programmed. So that information is removed, and the configuration bit stream size can come down. So that has two implications. One is that you can store it in a lesser memory space and it can be configured very fast. The configuration will take lesser time, otherwise for a fixed device it will take kind of fixed time. For the device is larger, it takes larger time, but even in a larger device if it is not used, only 50% is used, it might take kind of less time than the full FPGA configuration. Another possibility which is available is that suppose this addresses, suppose you have programmed a configuration here and the field, like if it is programmed in a flash and flash memory, and sometimes the flash can get corrupted. Suppose the flash get corrupted, then the whole device may not work, the flash need to be reprogrammed. Okay, nowadays it's possible, you would have seen that earlier the computers used to update through the internet, the drivers, the software and all that. But now you can see the set-top box at your home connected to a TV, it can update through the cable, through the cable the firmware get updated. Your mobile phone can get updated with the firmware over the air. So same thing can happen now, the configuration through the internet or wireless network can get get to the device and the device can reprogram itself. So that is a possibility. So but still in the field if the flash is getting corrupted, it will be a good idea if you have a kind of a golden bit stream or a fallback bit stream, which may not be the recent one, which may be a very old one which is stable. Okay, it may happen that you update the configuration over the internet and some corruption has happened, then you can fall back on a very stable version which is there from the beginning. Okay, so that is what is called multi-boot, and that is what is shown here in this particular slide. So you can have at least one main configuration and one fallback configuration, and during the configuration if the CRC error, like while the configuration bit stream is read, the CRC is calculated, if there is any bit corruption CRC will give error. In that case it will fall back on the golden configuration. Or if the sync word detection is timed out, that means at the beginning there is a sync word, and if that is corrupted and there will be a watchdog timer which is waiting for it, and if it does not come that times out, and in that case it can fall back, it can fetch the golden configuration from a particular location, and that can program the FPGA and can recover from that particular error. And this scheme of multi-boot is available only in the SPI based flash PROM and the BPA based flash PROM. Okay, so in both it is available. It's a very good option if you have a kind of, if you are deploying FPGAs in the field, you should think of the multi-boot, encryption and compression and all that, which will kind of improve the reliability, improve the security, all that part. Okay, now the current FPGAs, in addition to the DLL, PLL, block memory and all that, you have the DSP slices which allows the designer to implement the DSP algorithms very efficiently, and the DSP algorithm normally use fixed point computation, 18-bit Mandisa may be used. So there are and you know that in one of the major operation in signal processing algorithm is multiply and accumulate, so which requires a multiplier and an adder. Okay, so the DSP blocks, there is a Xilinx FPGAs DSP blocks give you this particular option. You have a pre-adder, that means there are 18-bit 2's complement pre-adder, that means you can do signed addition 18-bit in the pre-adder, and that added output can go to a multiplier which is an 18 by 18 multiplier. So two 18 bits can be added and that can go to multiplier. It can multiply another 18 bit which is coming from a separate port. It produces a 36 bit result. Now this can be sign extended to 48 bit and it is followed with a 48 bit 2's complement adder subtractor, and there are various, it's not that everything need to be used. You can use this multiplier along with the post adder, or you can cascade pre adder and post adder bypassing the multiplier. You can take the multiplier result outside 36 bit result. So all kinds of options are available in the DSP slice, which really enables one to implement the DSP like say filtering algorithms, the encoders, decoders and so on. All that can be implemented very efficiently in the DSP slices, and many a times you just use the multiplier operator, and then if the data size matches then it gets implemented in the DSP slices, or it can be instantiated and you can use it. So this is the general architecture. You have 4 ports, all are kind of pipelined, and you can see 2 ports are added. 18 plus 18 it give you 18 bit result which is combined with 18 bit to a multiplier. This output can be taken out or it can be taken to in another adder which is 48 bit. So this is sign extended, added with a sign extension, that output is available. So this helps in implementing the DSP kind of algorithms, and this is called DSP 48A1 slice in the Spartan 6. And in addition I must mention, I have not put it in the slide, but I should mention that the current FPGAs allows you to use the lookup table as a shift register, because the lookup table is normally, suppose a 4 input lookup table, you have 16 flip flops inside serving as a location. So that is connected in a chain and is available as a shift register. In this case it is called SRL16, and that can be chained to form SRL32 and even higher 64 bit shift register up to 256 bit in some kind of Spartan 6 slice, and that can be chained across. So that is you get a shift register implementation without using the flip flops of the slice, because the number of flip flops in a slice is limited, and we have seen in Vertex there are only 2 per slice, 4 in a CLB. So if you say implement kind of 16 bit shift register, then you will end up using 4 CLBs, but using 1 lookup table in a CLB you can implement a 16 bit shift register. So that is possible to implement. And one other very important thing with respect to FPGA, so I'm kind of discussing all what is remaining. One problem with the FPGA is that you have designed something in FPGA, you have verified, you have done behavioral simulation, timing simulation, everything, but the moment you put that design in FPGA, for whatever reason if something goes wrong you cannot, and if it is an internal signal you cannot kind of debug it, you cannot see what is happening inside. Okay. So what is done is that the FPGA vendors give you a logic analyzer circuit which is hooked to the JTAG. So now you can instantiate this logic analyzer IP along with your design, and the probes of the logic analyzer can be connected to the internal signal, and through the JTAG port there will be a software which is available at the tool side, at the PC side, and through the JTAG you can capture the waveform of the internal signal and you can analyze it, and like logic analyzer you can trigger, say it will be kind of crazy because suppose you have some kind of 8 bit data line you want to monitor, okay, and your clock is 200 megahertz, and in 1 second there will be kind of 200 mega kind of data passing over the data bus if it is clocked at frequency. Then to analyze that or to store all that there will not be enough memory. So you can, if you know that you have a kind of hint saying that what could be going wrong, on a particular data the error happens, then you can trigger on that data and capture some data around that trigger point or after the trigger point or before the trigger point. So if you have used logic analyzer, you would have heard saying that pre-trigger, post-trigger, pre-trigger 50% and so on. That it depends on how much you capture before the trigger, how much you capture after the trigger, and the analysis is always offline. It's not that you on a trigger point you capture some data and you analyze offline on the PC and try to debug it. So it's a great tool to, it's like once you have some complex circuit going to the FPGA to debug, this logic analyzers can have to be used, and the Xilinx call it Chipscope Pro and the Altera call it Signal Probe, and it's very easy now. Over the years it has become a very nice tool. Only thing is that it occupies, because this IP, this circuit occupies some kind of space within FPGA. So if you are not really floor planning the rest of the circuit, it can upset the timing performance of your design sometime, but then if you properly design floor plan, that's not a very serious issue because it doesn't occupy much space. So that is shown in a picture here. You have the FPGA board, you have FPGA. What is done is that this is the kind of the blocks you instantiate, like you have a ILA Pro, it's a logic analyzer Pro which has the Pro points which can be connected to the user port, and this is the one which is connecting to the JTAG, and on the PC side you have a software which on the trigger it captures the data, transfer it to the PC, and you can analyze and take action. So that is what is the signal probing does. So I am just showing the vertex pins. You have the global clock pins which is dedicated, which is used which is the input to the clock tree. The mode pin for selecting the mode of programming, dedicated pins. C clock which is the serial clock which is can be reused as a user IO, program done, init, busy, the parallel port, all that can be used. Once the programming is done, it can be used as kind of, this program pin is dedicated, but this init pin, done pin is dedicated, but these are can be used as user IO, and there is all these, these are programming pin, and there is this is a JTAG port which is dedicated. TMS is the mode select, TCK is the T clock, TDI is the data input, TDO is the data output. Then you have the internal VCC, IO pin VCC, the ground, and so on. So normally the FPGA, this is a scenario, you will have clock pins, you have some dedicated JTAG port, dedicated mode pins, and the programming pins, some are dedicated, most of it is kind of can be, once the programming is over, can be used by the user. Okay. So there is one point I want to mention here is something called one hot encoding, which is a state machine encoding which is used in FPGAs. This is you see this is the state machine block diagram. We have an XAID logic which is decoding the input and the present state, and or a 2 block diagram, enough of it. But what can happen is that we will take an example to kind of to put the background for the need of one hot encoding. Suppose you assume a finite state machine with 5 inputs, 18 state and 6 output. So when you have an 18 states, it means that you need kind of for binary encoding 5 flip flops, because it is greater than 16, less than 32, 5 flip flops are required, and there are 5 inputs. So if you look at the XAID logic, and it will get 5 input and 5 state variable. So there are total 10 input to the XAID logic. Okay, but you know that there are 5 flip flops, so there will be D4 to D0. Each of that may not use all the inputs. Okay, but we assume the worst case. Assume that in some case all the 5 inputs are used, less likely, but then let us assume the worst case. So and we assume that, so there are 10 input for a next state logic, and once again we assume the worst case in the vertex. That means we have seen that the 5 input function can be implemented by cascading, or 6 input or 7 input can be implemented with 2 4 input lookup table, but we assume again worst case for the for the sake of argument. So here we have 10 input next state logic. So for one CLB can implement 6 input lookup table by 2 4 input make a 5 input, 2 5 input make a 6 input, and so on. Okay. Now when you have a 10 input lookup table, that means that you need 16 CLBs, because you can implement one CLB can implement 6 input lookup table. So you need 2 for 7, 4 for 8, and so on. Okay. So you will end up with a 16 CLB. I definitely have kind of exaggerated it because it's not the case that all the inputs, all the next state decoding will require all the external input, and it is even if there are really 10 input for some kind of decoding, then that may not require the lookup table, which is 10 input lookup table. One can cascade, but assume for the worst case it happens, one can kind of come out with such a scenario. Then what happens is that this next state logic is spread in multiple CLBs, and the interconnection of that make it slow. So this clock frequency, which is the TCO plus T logic plus T setup, and we are talking about the logic delay of the next state logic, and that can become very high, and it can bring down the clock frequency of the state machine. And we have analyzed the data path, and we have tried to kind of be very aggressive in the kind of the timing of the data path. And suppose if you have designed a high performance data path, but if the state machine is slow, then nothing can work. So not a good solution. The problem here is made by the next state logic, which is very complex. Okay. So the question is how to kind of reduce the complexity of the next state logic. So if you look at it again, you come back to the slide, we have 5 inputs, 5 state variables. So the question is, can we reduce the number of state variables? So, and we have used a kind of binary encoding which necessitated a 5 flip flops for encoding 18 states. So why not encode 18 states in 18 flip flops? Okay. So while decoding, instead of decoding a state, when you decode a state, you don't need 5 bits representing that one state. You can take 1 bit representing that state. That is the basic idea. So you have there each state is a flip flop. Okay. So you take this kind of state transition like SJ get 2 transition, one from the previous state Si on condition I, and Sj there is a self loop which is condition J. So the Dj because this is nothing but the Sj, Dj corresponding to this state J is nothing but condition I and Si, but Si is just a single flip flop, so we will say it is Qi, or condition J which is composed of worst case 5 inputs and Qj, because this state is represented by a single flip flop Q. Okay, Qj. So you have the worst case 5 inputs specifying this input condition and 2 inputs for Qi and Qj. So you have 7 input next state logic which require only maybe 2 CLB which is less spread, and then we have less logic delay, and the timing, the clock frequency becomes manageable. Okay. That is the idea of one hot encoding. So there is many a times people blindly, like when you see FPGA you just say okay, let the state machine be one hot encoded. It is not required. Suppose you have a 4 state machine with 2 input and 2 output, absolutely there is no need to go for one hot encoding, because this can be encoded using 2 flip flops, and with 2 input the next state logic can go in one lookup table for a particular flip flop, and there is absolutely no need of going for 1 hot encoding. So but when the number of states are more, number of inputs are more, then you can go for 1 hot encoding, which eats up the flip flop, but the timing becomes better, which definitely is at the cost of extra flip flops, but the timing is better. So this can be kind of control using some kind of attribute in VHDL code. You can have a state encoding like sequential, which is binary, like the state 0 will have the 00, state 1 is kind of 1, and the gray is a gray code, and this is the 1 hot 1 and 1 hot 0, which is a single flip flop for a particular state, that is what is 1 hot 1 and 1 hot 0, and this can be controlled using some attributes, like saying, suppose you can say, suppose you have defined a state type called enumerated state type called state type, you can say attribute state encoding of state type, you can say type is gray or 1 hot 1, 1 hot 0 and things like that. Or you can even specify attribute enum encoding of state type, type is, you can say S0 is this, S1 is this, S2 is this, S3 is this, you can literally specify the state encoding, okay. And now this is the vendor dependent, this is not a part of the VHDL, this is a user defined attribute, so you have to refer to the vendor tool manual whether they support it, okay. So we are coming to the end of the lecture, so I will complete this part in the next lecture, maybe another 15 minutes I will be able to complete the FPGA part, then we will look at some remaining the VHDL part. So today basically we have completed the configuration, we have looked at what is implemented in the current FPGA in terms of the configuration, we have looked at the bitstream compression, bitstream encryption, multi-boot, then we have looked at this 1 hot encoding where the next state logic complexity can be reduced so that the state machine works with at a faster clock, so that the data path, it is in sync with the data path, and that 1 hot encoding can be controlled using some attributes. That is what we have discussed today, and what is remaining is very minimal. We will look at complete this part, and we will look at some FPGAs from other vendors very briefly, one from the Altera and one from the Actel, and wind it up. Please review the portions I have covered so that you are in sync, and I wish you all the best and thank you.